if you section this exactly on the front face, right face and so on, then you will get this. And here we are just showing you the same diagram that this center one is now this center one, right? So this center one is touching all of the corner ones all around. The coordination number is 8, but because it has pushed them away, therefore now this and this have a small distance and this have a small distance and so on. And if you had access to a package like SolidWorks or AutoCAD 3D and so on, and you drew this, that you have some sphere on all corners, say it is 1 centimeter, whatever size, and you have the balls and they are initially touching each other, but then you push one. So if you had actually done this and then say section this, then you will see and you can find what is the volume after cutting. Remember it has been cut on this face, it has been cut on this face, and it has been cut on the bottom face, isn't it? There was a sphere, but when you cut it on one face, if you cut a sphere on one face, you get half. Then you cut it on the other face, and then you cut it on the third face, right? So how much is there? Is it 1/4? Is it 1/3? That is to be found out. So here they are telling you that it is 1/8. We can actually measure it by geometry. Here it is enough for us to know that if we use the hard sphere unit cell where each sphere is touching each other, then there are 1/8 on the corners. So how many total atoms are there? There are 8 corners, right? 8 corners on the cube. So 8 into 1/8. And there is one full body centered. So there are 8, which is 1/8. This is 1, right? And then one body centered. So there are actually 2 equivalent atoms per unit cell. You initially think that there are 8 on the corners and 1 in the middle, but all the corner ones are only 1/8. So in effect, in terms of solid volume of the atoms, there are 2 atoms in a BCC unit cell. And how do we come up with a relationship between the radius of the atom and the lattice size A? A is one side of the cube. So I will request you to pause the lecture here. Do not look into any slide before or after. Take a piece of paper, blank, and try to draw a rough cube. And try to draw those circles which are touching each other, right? So now each circle has a radius of capital R, and the size of the cube, one side is A, the other side is A, the other side is A. So this is your diagram. You have a cube on all corners of the atom of the cube, and in the center there is one circle. And then the size, there are 2 sizes. The radius of each circle is capital R. The length of one side of the cube is A. So now try to cut the cube into a triangle, into something, so that you have from one center to the other center, what is the line, what is the length, so that you can come up with this type of an equation, yourself. So it is not something to be memorized. It is not something to be remembered. I keep on telling you, if you understand, then it will always be there with you. Even if you forget it, you quickly draw so right now, pause my lecture please and do that. And once you think you have done the basic geometry, then continue with the lecture, please. This is the configuration then, right? The BCC body centered cubic. This whole atom in the center is a full complete atom. And on all the corners, top, back, top, front, this one on the back, here, they are all corner atoms, right? So 4 corner atoms on the top, 4 corner atoms on the bottom, and in the middle there is this solid one. So if you try to draw it in a simple structure, the first thing is draw a nice cube. This practice you must have, that a straight line, 1 square, 2 square, join them, you get a cube. So there is a cube. Now don't draw all of them, just draw the central, the body centered. This is a full atom. And on any diagonal, this diagonal we are choosing, or that diagonal you could have chosen, any diagonal, draw the corner atoms. So we are just doing this, that we are drawing the body centered, the full center one in the middle, and one corner atom here, one corner atom here. Of course, if it's a corner atom, because of the cube we have cut it, otherwise this is a whole full atom here. So some portion of the atom is being shared by the other cells. So now if you think in terms of radius, that if the radius of one of them is capital R, then this is one radius, this is the diameter, so this is two radiuses, and this is another radius. So 1, 2, 3, 4. On this line you have 4R. If you look at the distances from another viewpoint, then it is a cube. So each side, this side is A, this side is A, this side is A, right? They are all A's, isn't it? So if you take the bottom face, then this is an A, this is an A. If you try to draw this diagonal from here to here, it is simple Pythagoras theorem. A square plus A square under root. So that will come out to be root 2A. A square plus A square under root. It will be root 2A. So because this is A and this is A, so on the base face, the diagonal is root 2A. Now think of another triangle. You are starting from here, you go there, then you go here, and then you come back here, right? So think now of this triangle, which is this diagonal, base diagonal, this and this. Now the base diagonal is root 2A. This side is of course A. So this length will be A square plus a square of root 2A, isn't it? If you square this, it will become 2A square, and this is A square. So this will become 3A squared. And if you take the root of that, it will be root 3A. So the length of this line is root 3A, right? Very simple geometry. You just start with the diagonal of the base, and then you go to the diagonal across, and you will find that this is root 3A. So now this line, this same line, in terms of radius is 4R, in terms of lattice constant A is root 3A. So this is your equation. Root 3A is equal to 4R. So it is as simple as this. It is just that you have a practice of drawing the cube, and in that cube you draw a central body centered atom and the corner atoms, and then you can get it. Now this is a remarkable thing. This is an equation which relates to the radius of the atom to the lattice constant in BCC, right? This is big. I mean, now it is such a simple thing for us, but people had been working on crystal structure for 20 years, 30 years, 50 years, so on, and until microscopes were there which could go to nanometer size, so much magnification that they can see nanometer size, until then crystal structure was not very clear and so on. But now, based on atomic theory, if you know the radius of an atom and you know that this material is BCC, then from this equation you can predict the lattice constant of the cube, that if it is a BCC, then this BCC, this metal which has radius of atom of so much, will have this lattice constant. This is remarkable. Of course, the theory is based on assumptions, right? Remember the solid atom assumption, that we are considering that each atom is a solid round ball, is a sphere, and that each atom in the lattice, in the unit cell, is touching each other. So now if we experimentally find this by very advanced microscopes, and from here we predicted by the equation, take the value of radius from the atomic theory, find A is equal to 4R upon root 3 and find the value. See if the experimentally found value from very high level microscopes is the same as this. If it is the same, then your theory that atoms are solid rounds and that atoms are touching each other were valid assumptions, right? So this is brilliant, and this is how science is done. Once we have done this basic thing, then we describe something like density, but at the unit cell level. So this is called atomic packing factor. Atomic packing factor is the volume of the atoms in the unit cell divided by the volume of the unit cell. Remember, there are atoms inside, isn't it? The central atom and the corner atoms. How many are there in BCC? 2 complete atoms. What is the volume of a sphere? From your basic geometry, remember, 4 by 3 pi r cubed. Remember, a sphere volume, not area. So it is 4 by 3 pi r cubed. That is there in your mind, hopefully. So if there are 2 atoms, then 2 multiplied by 4 by 3 pi r cubed. If you know the radius of the atom, then this is the volume of the atoms in the unit cell. And what is the volume of the total unit cell? It is a cube. It is a cube, and each side is A. So what is the volume? Yes, you are totally right, A cubed. So this is the volume of the unit cell, A cubed, and the volume of the atoms is 2 times volume of a sphere, right? So this is how you do it. Now, based on this, they are saying the atomic packing factor for every BCC, whether it is iron or chromium or any other material, if it is BCC, then this atomic packing factor is 0.68 or 68%. What does this mean? That in any BCC unit cell, 68% of the unit cell is filled with atoms, and that means 32% is empty, right? So this is big for you to understand, that this is sort of a density, as I told you, right? That the unit cell is there, the total unit cell, the box of A cube box is there. You fill it with atoms in a BCC manner. So 68% of the cubic cell is filled up with solid material and 32% is empty, right? So because 32% is empty, so we don't call it closed packed. For closed packed, it should be more packed than this one. We show a table now. This is a remarkable table. The first time you see that there are different metals. All these metals, chromium, iron, molybdenum, potassium, sodium, tantalum, tungsten, vanadium, very common engineering materials, most of them. The lattice constant A, the size A in nanometers, and the atomic radius R in nanometers. This is from the basic atomic theory that we have done in chemistry and physics. This is found experimentally. This is the real value, experimentally by XRD or something else at room temperature around 20 Celsius. If we increase the temperatures, atom will start to move and they will disturb the structure and the size can be different. But experimentally found lattice constants A and experimentally found atomic radius R are there for different atoms,